The sky above you is scattered with light, quiet, ancient stars blinking softly against the infinite dark. Each one a furnace, a living sun burning for 1 billion years. But even stars must sleep. Tonight we drift into what remains after that final breath, into the silence left behind when a star collapses and something stranger takes its place. Imagine a place so dense, so heavy, that atoms themselves collapse. A teaspoon of it would outweigh a mountain. These are not black holes, not yet, but something just as mysterious. Neutron stars, the frozen cores of long-dead suns. They do not shine, they do not burn. And yet, within a sphere no larger than a city, they hold more mass than our sun. Their gravity bends time. Their spin powers invisible beams that sweep through the cosmos. And though they are among the most powerful objects in existence, they are utterly, perfectly silent. If you could drift near one, you wouldn't see a flare or hear a sound. You'd feel time stretch, light bend, and your heart beat slow to match the rhythm of a remnant older than memory. These stars are time capsules. They hold the final whisper of stellar fire, sealed by gravity, encoded in spin and silence. Most are hidden, scattered across the Milky Way, quietly shaping the galaxy. And tonight, as your breath deepens and your body rests, we will follow them. We'll journey through their birth in the heart of dying stars, feel their magnetic storms and gravitational pulse, and listen to the ticking of pulsars echoing through space. No need to understand it all. Let your thoughts drift. Let the science become story. Before we begin our journey among the stars, I just want to say, if you enjoy this kind of quiet wonder, a simple like or a subscription means the world to a small channel like mine. It helps these stories reach others who need rest, curiosity, or just a moment of calm. Thank you for being here. So now close your eyes and let's drift onward. The stars are dimming, and in the quiet between thoughts, the neutron stars are waiting. Far above our quiet planet, where the air thins into space and even the silence begins to stretch, stars burn in equilibrium. These brilliant suns, scattered like fire across the night, are not just ornaments in the sky. They are engines of physics, colossal machines suspended in perfect balance. At their cores, a quiet war is always being waged. Gravity, eternal and patient, presses inward with unimaginable force, trying to crush the star into nothing. But deep within, nuclear fusion fights back. Hydrogen atoms, drawn into one another by immense pressure and heat, collide and merge into helium. This fusion releases a flood of energy. Photons and neutrinos burst outward, pushing against gravity's squeeze. The result is a delicate equilibrium. The star neither collapses nor explodes. It holds itself together, balanced between implosion and explosion, for millions, even billions of years. It glows not because it is dying, but because it is constantly resisting death. In this balance, the star lives a stable life, radiating light and heat into the darkness. From afar, it may look still, but inside every second is a flurry of collisions. In the core, temperatures climb to tens of millions of degrees. The particles move faster than sound can travel, smashing into one another in a fury of transformation. For stars like our Sun, the process is gradual. Hydrogen becomes helium. Later, helium becomes carbon, and the chain continues until it cannot go any further. But for stars many times more massive than the Sun, stars so large their light pulses across galaxies, the end comes suddenly, and with fury. As a massive star ages, its core grows hotter, denser, and more desperate to support itself. It burns through its fuel more quickly, like a candle exposed to wind. Each layer of fusion becomes shorter-lived. Helium fuses into carbon, then oxygen, then silicon, until finally it produces iron. And this is where the star meets its limit. Iron is the dead end of fusion. Unlike lighter elements, it does not release energy when fused. Instead, it consumes it. The fire that held back gravity begins to fade. Without fresh fuel to burn, the outward pressure collapses. Gravity, which had been held in check for millions of years, now wins. In less than a second, the core implodes. Picture it. a star dozens of times the mass of the Sun, collapsing inward at a quarter of the speed of light. The outer layers, once drifting in thermonuclear winds, now fall downward like an avalanche of burning gas. The core compresses to densities beyond comprehension. Protons and electrons are crushed together, forming neutrons. Neutrinos, ghostly particles born in the chaos, scream out in all directions, carrying away energy no other particle could. Then, with a recoil of titanic force, the star explodes outward. A supernova, brighter than an entire galaxy for a few fleeting days. Its light races through space, illuminating clouds of interstellar dust. Heavy elements forged in the chaos, gold, silver, uranium, are hurled into the universe. And what remains at the center of this detonation? Not fire, not light, but something new. Something small, heavy, and strange. A neutron star. The last breath of the star is not wind, but collapse. Not brightness, but density. Not a sunset, but the compression of physics itself. The layers fall away, and only the core remains. Dense beyond imagination, spinning silently in the void it helped create. We are not just stardust. We are built from these endings. Our bones carry the memory of stellar deaths. Our blood carries the iron made in the last moments of a star's collapse. And tonight, as you rest beneath the vastness of sky, you are cradled in the light of stars still fighting that ancient balance, and the remnants of stars that lost it. At the centre of a dying star just before the collapse, something extraordinary is taking place. Imagine, if you will, the innermost heart of a massive star, a region once stable and roaring with nuclear fire, now cooling, falling, and folding in upon itself. The temperature has reached billions of degrees. The iron core has grown large, but it cannot support itself. It can no longer produce the energy required to push outward. And then a threshold is crossed. The Chandrasekhar limit, a boundary that exists not in distance but in mass, about 1.4 times the mass of our Sun. Above this, electron degeneracy pressure, the strange quantum force that once held white dwarfs aloft, can no longer resist gravity's pull. In a moment less than a second long, everything changes. The core collapses, downward, inward, faster and faster. The very atoms are torn apart. Electrons, normally whizzing in their orbits, are shoved into the nuclei. Protons capture them, and in their union, they vanish, becoming neutrons and releasing neutrinos, those ghost-like particles that carry away the energy, like whispers escaping a scream. This is not just a chemical reaction. It is a quantum transformation of matter itself. The dense core compresses into a sea of neutrons. Nothing remains of its familiar structure. It becomes something almost alien, a nuclear fluid, dense beyond imagination, where even light struggles to escape. The collapse continues until the pressure becomes so great that the neutrons themselves resist further compression. This is neutron degeneracy pressure, another quantum wall, even stronger than that which resisted before. It is as though space itself says, no more. The infalling material slams into this wall of neutrons and rebounds outward with unimaginable force. This is the origin of the supernova shockwave, a sudden reversal, a cosmic whiplash. Outer layers, falling at tens of thousands of kilometers per second, are thrown back in a tidal blast of radiation and plasma. The core, now compacted into a sphere only about 20 kilometers wide, becomes a neutron star, a stellar corpse unlike anything else. It is smaller than a city, but denser than an entire solar system's worth of matter. It is the most violent birth in the known universe, and it happens in total silence. You would not hear the collapse. You would not see it with ordinary eyes. The moment of transformation is veiled in neutrinos, X-rays, gravitational waves. It is invisible to us, but not to the laws of physics. They unfold precisely, relentlessly. Each interaction, each particle, each boundary crossed is written into the ledger of the cosmos. And this is the miracle, that out of fire and fall a new object is born, not chaos but order. A neutron star does not flicker or rage, it remains, it stabilizes, it cools, and then it spins. Some rotate hundreds of times per second like gyroscopes powered by collapse. The energy of a dying sun now coiled into a spinning remnant, its magnetic field twisted into titanic loops, its surface rippling with exotic particles and theoretical states of matter. The core has failed, yes, but something has been created. Dense, eternal, strange. A monument to gravity's power and quantum physics' resistance. And now it waits. Drifting in the black, wrapped in invisible storms, the neutron star endures. Not burning, but glowing faintly, with the memory of its past. The collapse is over, but the story is not finished. Now comes the outward bloom, the release of everything that once held the star together. From the instant the shockwave rebounds outward, the star tears itself apart. Shells of gas, once held in place by fusion's push, are flung into space at 10,000 kilometers per second. Heavier elements forged in the star's final moments, iron, nickel, silicon, are hurled into the interstellar dark. It is not merely destruction, it is distribution. It is how the universe sows its seeds. What you would see if you could watch this unfold is breathtaking. A single point of brightness, flaring suddenly in the night, outshining entire galaxies for a few brief days. This is a supernova, a single star collapsing and exploding, shining brighter than hundreds of billions of suns combined. The light travels for thousands, sometimes millions of years, before it reaches us. And even then we see only a pale echo of its true power. Long after the light fades, the debris continues to drift. Over decades and centuries, it expands into a glowing cloud, an intricate lace of filaments and knots, heated by the fading radiation of the blast. This is a supernova remnant, and in telescopes they appear like cosmic jellyfish or gossamer webs suspended in the void. The most famous of these is the Crab Nebula. Once a star in the constellation Taurus, it exploded in the year 1054. Its light so bright that Chinese astronomers recorded it shining in daylight for weeks. Today we see its remains, a glowing, writhing mass of ionized gas, stretching light years across. And at its heart, almost invisible, lies the source of it all, a pulsar. This is the neutron star left behind, now spinning hundreds of times each second, sweeping out beams of radiation like a cosmic lighthouse. As it rotates, those beams pass across Earth, creating regular pulses of light and radio waves. It is not flickering, it is spinning so rapidly that a single grain of sand on its surface would be moving faster than a bullet. These pulses are how we first discovered neutron stars, tiny regular blips in radio telescopes, so precise that the first astronomers who observed them thought they might be signals from alien civilizations. They labelled the first source LGM1, Little Green Men. But it wasn't life. It was the voice of death, echoing across space. The neutron star remains buried in the remnant, invisible to the eye, but not to science. We now use radio, X-ray and gamma-ray telescopes to trace their presence. And what we find again and again is the same story. A star lived, a star died, and something impossibly dense was left behind. Over time, the nebula fades. The expanding gas cools, dissipating into the interstellar medium. But the neutron star remains, spinning, cooling, aging. It will take millions, even billions of years to slow. And even then, it does not disappear. It merely goes quiet, its radiation falling beneath detectability. But it is still there, a stone in the river of space, a fossil in the night. The remnants of stellar collapse are not gone. They become part of the next generation, clouds that form new stars, planets and life. We live in the fallout of supernova, the calcium in your bones, the iron in your blood, the gold on your hand. All of it was forged in the death throes of stars. The neutron star, once at the heart of fire, now rests. It has no wind, no light, but it is not empty. It contains memory. The memory of pressure and collapse and the stillness that follows creation. So when you look at the night sky, know this. Some of the stars you see have already died, their light only just arriving, and some of the empty places, the places without stars, are not truly empty at all. They are where the neutron stars live. In the heart of the dying star, collapse has finished its work. The light has gone, the blast has passed, and what remains is something new, something neither living nor dead. The birth of a neutron star is not a loud event. It is not a celebration. It is a transformation hidden inside the explosion, the quiet forming of a remnant that obeys laws more strange than we're used to. Imagine a sphere no larger than a city, perhaps 20 kilometers across, floating in the blackness of space. It weighs more than the sun, not in pieces, not scattered, but all of it, compressed into a single place. The outer layers of the star are gone, blown apart in the supernova, but the inner core has resisted complete collapse. It has become something else. A neutron star is not made of atoms in any form, you know. The heat and pressure at the moment of collapse was so intense that electrons were squeezed into protons, forming neutrons, the neutral particles that usually rest deep inside atomic nuclei. But now, freed of their usual cage, the neutrons are packed together like a fluid of stone, shoulder to shoulder, with almost no space between them. If you could scoop a single teaspoon from the surface of a neutron star, it would weigh over 1 billion tons. That is not poetry. It is physics. That same spoonful would outweigh every car on Earth combined. But how can something so small be so heavy? It all comes down to density. Matter is mostly empty space. The atoms in your body, the air you breathe, even the walls around you, are mostly nothing. The nucleus of each atom is tiny, and electrons orbit at great distance compared to their size. But in a neutron star, that space is gone. The structure of atoms has been obliterated. The electrons have been swallowed, and what remains is pure nuclear matter. Not just a nucleus, but a city-sized mass of nuclei crushed together into a single, unbroken mass. This is not a place where molecules survive. There are no crystals, no cells, no light bouncing through air. The surface may be made of an exotic solid crust, iron atoms flattened into sheets by gravity, their electrons stripped away. Beneath that, the neutrons form a fluid, or perhaps something stranger. We are not yet certain. As you drift through this dream of physics, imagine the layers. At the outer edge, a crust of compressed ions, frozen in place by gravity billions of times, stronger than Earth's. Beneath that, a sea of degenerate neutrons, so tightly packed that their positions blur together, forced apart only by the rules of quantum mechanics. Deeper still, strange possibilities begin to emerge, hints of exotic particles, perhaps even quark matter, where neutrons themselves dissolve into their components, up and down quarks flowing freely in a kind of nuclear ocean. These are places no laboratory can reach. They are only modelled by equations and glimpsed through the echoes of distant stars, and above it all a magnetic field billions of times stronger than Earth's. If you were somehow near it, the field could twist your molecules apart. Light behaves differently here. Atoms are stretched. Space itself is distorted. But you are safe. You are only imagining. The birth of a neutron star is a kind of resistance, the last stand of matter against collapse. It is where quantum rules push back against gravity, where the Pauli exclusion principle, the rule that says no two fermions can occupy the same state, becomes the only thing holding the star up. It is not will, it is not choice, but it is a kind of defiance. And in that defiance, a new form of object is born. A frozen engine of gravity, glowing faintly with residual heat. Its spin a memory of the massive star it once was. It may spin dozens, hundreds of times per second, its angular momentum conserved, concentrated, wound tight by collapse. The result is a beacon, not of light but of physics. And so, in the quiet aftermath of destruction, a new world is formed. Not a world of oceans or skies, but one of neutrons, gravity, and strange magnetic storms. A place where the known rules begin to bend, and it all begins with collapse. Beneath the thin veil of emptiness that separates a neutron star from the rest of the universe, lies a realm of matter so extreme that our language struggles to describe it. The surface, if it can be called that, is not like the surface of a planet, or even a white dwarf. It is a crust of pure atomic strangeness. Crystalline iron stripped of electrons, arranged in rigid sheets that barely cling to the gravity-soaked shell beneath. This outer crust is only a few hundred meters thick, but in that thin band lies pressure enough to crush atoms flat. Gravity here is so strong that if you dropped a pebble from just a few meters above, it would strike the surface with more energy than a speeding bullet. There is no gentle landing, no wind, no atmosphere, just an immediate confrontation with a wall of nuclear force. And yet, even in that unimaginable pressure, structure remains. Beneath the crust, the neutrons begin to ooze. They drip out of the nuclei like water squeezed from a sponge, forming a sea of free-floating particles, a neutron drip layer. Here, protons and electrons still exist, but only barely. They have been forced into unstable arrangements, existing only because the universe has nowhere else to put them. As we journey deeper, we enter what physicists call the inner crust, a region where the competition between nuclear forces and gravity produces bizarre geometries of matter. Some call it nuclear pasta, not for whimsy, but because the neutrons and protons form twisted, tangled shapes, spaghetti-like filaments, lasagna-like sheets, gnocchi-like blobs, the most energy-efficient configurations under these pressures. They are not fiction. They are predicted by quantum chromodynamics and nuclear simulations, and their presence changes how sound travels, how heat flows, even how the neutron star spins. Below this layer, the transition completes. We arrive at the core, a superfluid ocean of pure neutrons. There are no longer atoms here, only the neutrons themselves, packed so closely that quantum effects become dominant. They flow without friction. They rotate in vortex arrays. Some may even pair into exotic condensates, a kind of neutron superfluid whose properties defy ordinary matter. This ocean is not still. Inside, enormous forces churn and ripple. Temperature gradients, magnetic fields, and rotational shear can all lead to sudden dramatic shifts, like starquakes, events where the crust cracks or realigns, sending out ripples of X-rays and gamma rays across the galaxy. These quakes are not tectonic. They are quantum in nature, sudden shifts in the dense lattice of matter itself. Deeper still, the questions multiply. What lies at the very centre of a neutron star? We do not yet know. Some models suggest a quark-gluon plasma, a state of matter not seen since the earliest moments of the Big Bang. Others propose hyperons, particles heavier than neutrons, or condensates of kaons and other exotic forms. There may be no surface to speak of, only a seamless transition from crust to core, from strange to stranger. The pressure at the centre is so immense that if the star were only slightly more massive, it would collapse entirely into a black hole. But it doesn't. Not quite. It teeters on the edge, frozen between possibility and finality. This is the secret of the neutron star. It is not just a remnant, it is a boundary object, balanced perfectly between what can exist and what cannot. It is the densest form of matter the universe can support without tearing a hole in space itself. And in that knife-edge balance it endures. From the outside, it may look like a silent sphere, dark against the stars, but inside it is alive with tension, with forces that shape galaxies, with mysteries we still don't fully understand. Its mass curves the space around it. Its magnetic field sculpts invisible pathways through the interstellar medium. Its pulse, if it spins, echoes across time. And yet it remains still, compact, perfect in its restraint, a monument to what matter becomes when it has nowhere else to go. The neutron star has formed, its structure is stable, its collapse is complete. But even in this dense cradle of silence, motion remains. The star, now tiny in size but massive in memory, begins to spin, and not slowly. During the collapse, its radius shrank by a factor of thousands. Just as a figure skater spins faster by pulling in their arms, the neutron star conserves its angular momentum, spinning faster and faster until the rotation becomes dizzying. Some newborn neutron stars spin dozens of times per second, others, hundreds. The fastest we've observed rotate over 700 times per second. their surfaces moving at a significant fraction of the speed of light. And still, they hold together. Their gravity is strong enough to bind that furious motion into place. And with that spin comes a pulse. If the neutron star's magnetic field is angled just right, it channels radiation out of its poles in focused beams. These beams sweep across space like the searchlight of a cosmic lighthouse. And when they pass over Earth, we see a blink, a regular rhythmic tick that does not waver. We call these neutron stars pulsars. From the ground, we first saw them as brief, sharp pulses of radio waves, so precise, so regular, that the first one was mistaken for a possible alien signal. But we now know it is not life. It is the death of a star speaking in code. The light is not produced by heat, but by acceleration. The intense magnetic fields, trillions of times stronger than Earth's, whip particles into motion, accelerating them to near light speeds. These particles emit radio, X-rays, and sometimes even gamma rays. The pulses are a byproduct of this rotation, this furious dance of matter and magnetism. But not all neutron stars behave the same. Some are born with magnetic fields so intense, so violent, that they bend even the vacuum of space. These are magnetars, rare neutron stars whose magnetic fields reach levels no other known object can match. A single magnetar could erase the magnetic strip of a credit card from hundreds of thousands of kilometers away. If you stood near one, which you couldn't, your very atoms might stretch apart. These stars are unstable, prone to starquakes and magnetic flares, events that unleash bursts of energy, rivaling entire stars. And yet, they do not break. They remain intact, suspended between pressure and physics. Over time, the neutron star cools. The heat left over from its formation radiates slowly into space. It glows in X-rays, sometimes invisible light, but this fades. It becomes a cold ember, spinning still, silent now, unless its magnetic field is just right. Then it may sing for millions of years longer. And when even that fades, when the spin slows and the pulses vanish, the neutron star remains, a monument in the dark, no longer seen but still present. Floating quietly in the space between stars, it carries within it the memory of collapse, the geometry of quantum matter, the fingerprint of a sun that once was. Neutron stars are not just remnants, they are record keepers. They contain data encoded in spin, in heat, in motion. They tell us how massive their parent stars were, how fast they spun, what the final seconds of life looked like. And when they merge with one another, in the far future, they will produce new waves, ripples in the fabric of space-time, heavy elements cast into the void, and perhaps even stranger stars. But that is a story for another night. For now the neutron star spins on, alone, dense, eternal. The pulse fades from view, the field begins to weaken, and in the soft quiet between its rotations, there is rest. Close your eyes for a moment, and imagine holding a spoon in your hand. Not an ordinary spoon, a spoon filled with something strange, not soup, not soil, not stars, just one single scoop taken from the surface of a neutron star. It is silent. It does not glow. But if you could bring it here to Earth, it would fall through the table, through the floor, through the crust of the Earth itself, sinking like a stone through butter, crushing everything beneath it. That single spoonful would weigh 1 billion tons. That is not a metaphor, not poetry. It is physics. This is what we mean by density, a measure of how much mass exists within a given space. And in neutron stars, density reaches its ultimate form. You are no longer dealing with atoms as we know them. You are holding a remnant of collapse, a city-sized object packed with the mass of a star, squeezed into a space barely wider than Manhattan. At the surface, the density is already unimaginable, around 10 million tons per cubic centimetre. But deeper in, it rises further, climbing to nuclear densities, where the core contains more matter per volume than any known substance in the universe. To understand this, consider your own body. You are made of atoms, and atoms are mostly empty. The nucleus is incredibly small, and the electrons orbit far away in comparison. That empty space gives matter its familiar shape. Wood is soft, steel is strong, But even the hardest material is mostly vacuum, structured and stabilized by electromagnetic force. But in a neutron star, all of that space has been erased. The atomic structure has collapsed. The electrons have been absorbed into protons, forming a sea of pure neutrons, each one touching its neighbor, shoulder to shoulder, compressed until quantum pressure alone keeps them from merging. The matter no longer resists through molecular rigidity, but through the laws of quantum degeneracy. It is matter held up not by structure, but by principle. The Pauli exclusion principle, written into the fabric of quantum mechanics, forbids identical fermions, like neutrons, from occupying the same state. They can be close, but not quite the same. That microscopic rule becomes the force that holds a neutron star open. No pressure known to nature can push further unless gravity wins again, and the object collapses into a black hole. For now, though, the neutron star balances at this edge. We are standing at the limit of what matter can be. And yet it's more than just pressure and weight. Density here changes how space behaves. Light curves around the star like water swirling around a drain. Clocks run slower. A beam of light fired upward loses energy, climbing out of the gravitational well. Even time is stretched, diluted by the mass. In a way, to be near a neutron star is to be near the edge of the known. Gravity is just shy of total dominance. The curvature of space-time is steep, the equations precariously balanced, and the mystery only deepens the further you go inside. But for now, rest with this image, a spoonful that outweighs mountains, a star collapsed into silence, and a remnant that contains more reality per inch than anything else we know. Past the outer crust of iron and frozen ions, past the neutron sea that flows with quantum silence, and into a realm we cannot yet see, but only imagine, a realm where matter is so compressed that it may no longer resemble anything we have ever touched or built or known. We are now entering the core of the neutron star. Here the pressure is beyond anything the human mind was ever meant to comprehend. The density is so great that the very identity of particles begins to shift. The familiar world of protons and neutrons, those comforting building blocks of atoms, may start to fall apart. And what lies beneath? Some theories suggest a state called quark matter, a fluid not made of neutrons, but of the particles that compose them. Neutrons and protons are not indivisible. They are made of quarks, bound tightly together in groups of 3. But in the crushing depths of a neutron star's core, those bonds might break. The neutrons themselves could dissolve, becoming a quark-gluon plasma, a sea of free-floating quarks, and the force-carrying gluons that usually hold them together. This is not just dense, this is primordial, a reversion to a state of matter that hasn't existed since the first few microseconds after the Big Bang. In those ancient, early moments, the universe itself was hot and dense enough to sustain quark matter. And now, billions of years later, that state may still exist, hidden in the heart of collapsed stars. There are other strange possibilities. Some models suggest that inside the deepest layers, hyperons might form, particles even heavier than neutrons, made with strange quarks. These particles would normally decay in a fraction of a second, but here, under extreme pressure, they may persist. There may even be condensates of kaons, exotic bosons that shift the balance of mass and pressure in ways we still don't fully understand. These are not wild guesses. They emerge naturally from the mathematics of quantum chromodynamics, the theory that describes how the strong nuclear force binds matter together. But the conditions to test these ideas on Earth don't exist, not yet. The problem is, we cannot look inside. We cannot cut open a neutron star and peer at its center. We cannot sample its core or recreate its density. All we have are equations. And the signals that reach us, pulses, heat, gravitational waves, subtle shifts in spin, the rest is inference, but in that uncertainty lies wonder. The core of a neutron star is not only the densest material in the universe, it is a laboratory, locked away in the cosmos, running experiments with states of matter we cannot make. Every neutron star is a kind of archive, a vault of physical truth sealed by gravity, and the laws it obeys may not be complete. We believe that quantum pressure holds up the star, that beyond a certain mass it must collapse into a black hole. That matter can only be compressed so far before something gives. But what if we're wrong? What if the universe allows even stranger stars, ones made entirely of quark matter, or hypothetical particles that we haven't yet discovered? What if neutron stars are only one rung on a ladder that descends deeper and deeper into the fabric of reality? These questions remain open. What we do know is that inside these remnants of collapse, the known world has ended. The atoms are gone. The periodic table has lost its relevance. What remains is matter in its most extreme, most primal, most compressed form. And it is still. Not in the sense of absence, but in perfect containment. The energy is vast, but it does not burst. It hums silently, wrapped in pressure, cloaked in darkness. But for now, listen. There is no sound, no light, only a mass of pure memory, resting at the edge of possibility. From the outside, a neutron star is a sphere, small, dark and silent, adrift in the void. But its shape tells only part of the story. The real strangeness lies not in the star itself, but in the fabric of space surrounding it. Gravity, as Einstein revealed, is not a force that pulls, but a bending of space-time itself. Mass tells space how to curve, and neutron stars curve space with a depth that defies common sense. The mass is so concentrated, the radius so small, that the geometry of the universe begins to twist. If you stood on the surface of a neutron star, if somehow, impossibly, you would feel weight unlike anything on Earth. Not in tons, not in g-forces, but in the pure crushing warping of space-time. A small step would take infinite energy. A jump would be impossible. Even light would struggle to escape. And more strangely still, time would slow. To a distant observer, your clock would tick slower than theirs. Your voice, if it could travel, would stretch and deepen. Your heartbeat would dilate. Your movements drawn out like a dream in slow motion. This is not imagination. This is gravitational time dilation, predicted by general relativity and confirmed by observation. Clocks in stronger gravity run more slowly, and on the surface of a neutron star, gravity is so extreme that time itself becomes warped, like a rubber sheet drawn to the edge of tearing. The spin of the star also affects the space around it. Neutron stars rotate rapidly, some hundreds of times per second, and this motion drags space-time with it. Like a whisk stirring honey, the rotation twists the surrounding geometry. This phenomenon, called frame dragging, means that even space itself begins to swirl. And then there are the ripples. When two neutron stars orbit one another, their immense masses disturb space-time, sending out waves not of light, not of sound, but of geometry itself. These are gravitational waves, and they move through the universe at the speed of light, stretching and compressing everything in their path. When two neutron stars spiral inward and collide, they create some of the strongest gravitational waves we've ever detected. Instruments on Earth, like LIGO and Virgo, are so precise they can measure these ripples from billions of light years away, movements smaller than the width of a proton. We heard them for the first time in 2017. Two neutron stars collided in a distant galaxy, and for the briefest moment the Earth trembled ever so slightly. We had no eyes to see it, but the instruments recorded the whisper. And in that whisper, we heard the music of density, the voice of matter falling apart, the end of two stars, and the beginning of something else. The collision released not only gravitational waves, but light. A kilonova, a rare, powerful burst of electromagnetic radiation, scattered heavy elements into the cosmos. Gold, platinum, uranium, the atoms in your jewelry, your electronics, even your DNA, may have been born in that moment, billions of years ago, in the collision of two neutron stars. And it all comes back to density. Without it, the stars would not collapse. Without that pressure, space-time would not warp. The waves would not form. Time would not bend. The elements of life would not be forged. So the next time you look up at the night sky and see nothing, remember, there are places where space is folded and time slows, where the universe curves around the memory of a dead star. These places are quiet, invisible, but they are real, and they are waiting. But for now, rest in this knowledge. There are objects in the universe so dense, so strange, that they change the shape of reality itself, and they do it in perfect stillness. Imagine for a moment the final breath of a dying star. Its fuel is gone. Its fusion furnace, the engine that held gravity at bay, has gone cold. And gravity, patient and relentless, begins to win. The outer layers collapse inward. The core folds under its own weight. In less than a second, the heart of a giant becomes something new and something strange. This is not just a dead star. It is a neutron star, a city-sized object with the mass of the sun, compressed into a sphere no wider than Manhattan's. An object so dense that a single teaspoon would weigh more than 1 billion tons. We call it a star, but it no longer shines by fusion. It no longer burns. Instead, it holds, it balances. It becomes a frozen scream of gravity, pressure, and matter pushed to its limit. What stops it from collapsing further? Not thermal pressure, not chemical bonds, but something deeper, the degeneracy pressure of neutrons. In this compact prison of gravity, atoms are crushed, electrons and protons are squeezed into neutrons, and those neutrons, under quantum law, resist being in the same state. This resistance is what holds the star up. It is not strong in the usual sense, it is subtle, quantum, quiet. But it works. Inside the neutron star, structure is everything. The outer crust is made of iron-like nuclei arranged in tight lattices. As you descend, the pressure rises. Electrons are stripped away. Nuclei dissolve. Neutrons drip from atoms like water from melting ice. Deeper still, the star becomes a sea of free-floating neutrons, a quantum fluid with exotic behavior. It is no longer normal matter. It is something else. At even greater depths, we reach the inner core, a place of speculation and mystery. Some models suggest it may contain hyperons, particles stranger than neutrons and protons. Others propose quark matter, where even neutrons dissolve into their fundamental building blocks. No laboratory on Earth can recreate such conditions. Only nature, in the death of a massive star, can build a chamber of such pressure. And all of it is held inside a sphere no bigger than a city. The gravity here is so intense the escape velocity approaches half the speed of light. Time itself slows near the surface. Light bends and struggles to escape. A photon launched outward curves and weakens as it climbs. To a distant observer, the star appears dimmer than it truly is, not because it lacks heat, but because gravity stretches its light. This is gravitational redshift, and it is not just theory. We can measure it. The star is dim not because it is dying, but because it is trapped in a deep well of space and time. And it doesn't sit still. Most neutron stars spin. They rotate rapidly, like tops spun by collapse. Some spin once every few seconds. Others, the millisecond pulsars, can rotate hundreds of times each second. And as they spin, they carry magnetic fields billions of times stronger than Earth's. These fields, twisted by motion, power beams of radiation that pierce the cosmos like searchlights. A star collapsed, its fire extinguished, yet its presence never stronger. A sphere of neutrons, dense enough to bend time, and perfectly, eerily, still spinning. Though it no longer burns with fusion, the neutron star is far from quiet. It spins, it pulses, it screams through space in electromagnetic song. Wrapped around its dense body is a magnetic field so intense it defies ordinary understanding. This field, inherited from the parent star and compressed into a much smaller volume, is strengthened to unimaginable degrees, trillions of times stronger than Earth's. The field lines twist and coil, anchored in crusts of iron and neutron-rich matter, and as the star spins, those fields twist with it. When aligned just right, this magnetic geometry funnels radiation outward in focused beams. The neutron star becomes a lighthouse, not of visible light, but of radio waves, X-rays, and gamma bursts. These beams sweep through space as the star rotates, and if Earth lies in their path, we detect regular pulses. This is the pulsar, a dead star transformed into a galactic clock, sending out signals as constant and reliable as the tick of an atomic watch. Some spin once every few seconds. Others, the millisecond pulsars, have been spun up by stealing material from companion stars, reaching rotational speeds that would tear ordinary matter apart. But here, in the rigid structure of neutronium, speed becomes silence, precision, endurance. And yet, even these are not the most extreme. A rarer breed of neutron star, with even more violent fields, behaves differently. These are the magnetars. Their magnetic fields are so strong they distort atomic structures, crack the crust, and occasionally realign with sudden seismic force. When this happens, the star flares, releasing short, sharp blasts of high-energy light, bursts that can outshine entire galaxies for a fraction of a second. The star itself doesn't explode, but its outer layers convulse, sending ripples of radiation across the void. We have witnessed these flares. One in 2004 came from a magnetar halfway across the Milky Way. For a brief moment, it became the brightest object in the sky after the Sun. Its gamma ray burst ionized Earth's atmosphere and triggered detectors on multiple satellites. This was a whisper from a tiny invisible remnant of a star, speaking across 50,000 light-years with the energy of 100,000 suns. And we heard it. This is the paradox of neutron stars. They are the smallest stellar objects, yet among the most powerful. They are invisible to the eye, yet among the brightest sources in the sky. They are dead, yet they pulse with more order, energy, and electromagnetic life than most stars ever achieve. They sit at the edge of collapse. Add just a little more mass, and even neutron pressure can no longer hold. The crust cracks, the core folds inward, and a black hole is born. Nothing, not even light, can escape. But before that point, there is balance, perfect and fleeting. Neutron stars exist in that sliver of physics where gravity and quantum rules hold each other in check. They are nature's limit cases, the last stronghold before the void. And somehow, they endure. They spin in silence. They beam across darkness. They measure time and test the laws that govern everything. A sea of spinning cinders, each one small as a city, heavy as a sun, trapped in gravity's deepest well, and still sending light. Long after a star has died, the sky remembers. Though the light of the supernova fades within weeks, something lingers, a quiet afterglow, not always seen, but deeply felt. These lingering signals are the star's final words, carried not in fire but in rhythm, in invisible pulses that sweep through the cosmos. Some are slow murmurs in radio waves, others arrive as brief flashes of X-ray or gamma light. But all are real, all carry meaning, and together they speak of what remains after the fire. When astronomers gaze into space, they do not only look, they listen. High above Earth or buried beneath its surface, great detectors collect whispers from collapsed suns. These are not random. In the silence there is pattern, precision so exact that the stars themselves become clocks. That's how we first found them. Not as lights, but as beats. In 1967, the first pulsar was detected, a rhythmic signal, sharp, steady, arriving every 1.337 seconds. It was so precise that astronomers suspected an intelligent origin. They jokingly named it LGM-1, short for Little Green Men. But the truth was more astonishing. It was the heartbeat of a neutron star, spinning through space, sweeping its beam across Earth like a celestial lighthouse, a relic of collapse, now speaking in perfect time. Since then, we've found thousands, each one a neutron star with a magnetic axis tilted just enough to send a beam of radiation into space. If Earth happens to lie in its path, we catch the signal as a pulse. These stars rotate at astonishing speeds, some hundreds of times per second, and because they are so dense, their spin barely changes. Even over millions of years, their timing remains precise. These are the pulsars, silent, spinning remnants built in the death of stars, now acting as some of the most stable clocks in the universe. With them, we study space and time. With them, we listen to the dead. But not all echoes are gentle. There are neutron stars with magnetic fields 1,000 times stronger, so intense that they can warp atoms and tear the very vacuum. These are magnetars, and they are not quiet. Their surfaces crack and quake under pressure. Their fields twist and snap like solar storms gone mad. When they flare, they release massive outbursts of energy, X-rays and gamma rays so intense they can be seen across the galaxy. In 2004, one such flare erupted from a magnetar 50,000 light-years away. In a tenth of a second, it released more energy than the Sun will emit in 100,000 years. The flash was so bright, it momentarily ionized Earth's upper atmosphere. Instruments around the world detected it instantly. A reminder of how much power remains, even in death. These are the voices of neutron stars, not the blast of the supernova itself, but the enduring signal, the cold echo of heat, the structure that outlives chaos. And across the electromagnetic spectrum, we are building instruments to hear them better. Radio telescopes pick up the low murmur. X-ray satellites catch the sharp spikes. Together, they allow us to map what the eye cannot see. Now we will journey deeper into these cosmic timepieces to see how pulsars help us test gravity, measure spacetime, and prepare for a future where their rhythm may guide us across the stars. But for now, let this rhythm settle into your breath. The universe is not silent. It is filled with clocks ticking in the dark, and somewhere out there, another one just turned. Again. Imagine a clock, not one built of gears or circuits, but of collapsed matter and magnetic light. A neutron star, spinning in the aftermath of a stellar death, sending out pulses of radiation with each perfect rotation. These are not fragile machines. They are cosmic metronomes, born in fire, steadied by gravity, and ticking with astonishing regularity. Some pulsars spin faster than a kitchen blender, hundreds of times per second. We call them millisecond pulsars, and they are among the most stable timekeepers in the known universe. Their pulses do not drift, they do not fade. Some have been monitored for decades and vary by less than a millionth of a second. They're so consistent that astronomers now use them the way sailors once used to stars. As navigation beacons, as deep space clocks, as lighthouses floating in the void. These pulsars have become tools. One of the most profound discoveries came from a binary system, two neutron stars orbiting each other. One was a pulsar. Its clock-like pulses allowed scientists to track its position with extreme precision. And over time, something strange emerged. The two stars were spiraling inward, slowly, invisibly, losing energy. But where was the energy going? The answer, predicted by Einstein, lay in gravitational waves, ripples in space-time that radiate outward from massive accelerating bodies. Though undetectable at the time, the shift in orbital timing matched the theory perfectly. This was the first indirect confirmation that gravitational waves were real. The discovery earned a Nobel Prize, all from watching a dead star keep time. Now we listen with even greater attention. Projects like the Pulsar Timing Array track dozens of these neutron star clocks scattered across the galaxy. If a gravitational wave from a distant supermassive black hole were to pass through, it would stretch and squeeze space just enough to shift their pulses. Not all at once, but in a pattern, like a wave sweeping through a net of light. This is how we now study the deep fabric of the cosmos, not with collisions in labs, but by listening to the heartbeat of stars long dead. And it doesn't end there. These signals may one day guide our spacecraft. As humanity reaches beyond Earth and solar system, we will need new ways to find our place. GPS cannot reach beyond the planets, but pulsars can. Their pulses are unique, predictable, and stable. A map of known pulsars could allow interstellar explorers to navigate through the galaxy using the rhythm of neutron stars alone. But even as they guide us, they still surprise us. In 2007, astronomers detected a strange new kind of signal, a fast radio burst, lasting only milliseconds, bright and unexplained. Since then, hundreds more have been found. Some repeat, others do not. Some come from known magnetars, others seem to arrive from deep intergalactic space. Their origins remain mysterious. Are they flares from neutron stars, mergers, something new entirely? We are building better ears, instruments like CHIME and the Square Kilometre Array, to catch more of these sudden cosmic flashes. Each new signal is a clue. Each burst is a question. Even in our own Milky Way, most neutron stars are still invisible, hidden behind dust, beams pointed away from Earth, waiting in silence, and some may be unlike anything we've imagined, rotating strangely, or not at all. And so we keep listening, through gravitational detectors, through X-ray observatories, through arrays of radio dishes, scanning the heavens, night and day. We study pulse shape, frequency, timing. We map the interior of stars we cannot see, using only their light and rhythm. What lies at their cores? Do they contain quark matter? Do the laws of physics behave differently under such pressure? We do not yet know. But the questions themselves are beautiful, because each pulse, each flare, each echo in the dark tells us something new, not just about stars but about time and matter and the shape of space itself. Far from our world, in the silent dark between the stars, two tiny corpses of collapsed suns begin their final dance. They are neutron stars, dense, dark, and nearly invisible. Alone, each is a monument to collapse, but together they are a clock winding toward a cosmic event unlike any other. Their orbit is tight, their mass immense, and with every passing moment they spiral closer. They do not shine, they do not burn, but they ripple. Their motion stirs the fabric of space itself, sending out gravitational waves. These are not waves of light or sound, but of geometry, ripples in the shape of reality. As the stars orbit each other, they shed energy through these waves. Slowly, imperceptibly, the orbit decays. The spiral tightens. What began as a slow waltz now quickens to a frantic pirouette. The two stars, each no wider than a city, move faster and faster, racing around one another hundreds of times each second. Their surfaces distort, pulled into teardrop shapes by tidal forces. Matter stretches, magnetism surges, and time itself begins to bend. In their final second, the distance between them shrinks to mere kilometers. Velocities approach a third of the speed of light. The stars tremble with pressure, their interiors cracking, their fields snapping. The gravitational waves swell to a crescendo, the loudest whisper the universe can make. And then they touch. The impact is not an explosion in the way you might imagine. It is a convergence, a collapse, a release of energy that transforms the surrounding space. Some matter is ejected in thin arcs, rich in neutrons and raw nuclear fuel. Other parts crash inward, forming a hypermassive object that may persist for milliseconds before collapsing further. A kilonova is born. The energy released in that instant rivals all the light in the observable universe. For a moment, the darkness is peeled back. Radiation floods outward, X-rays, gamma rays, and light in every color. The ejected matter begins to cool and condense, undergoing rapid neutron capture, a process that creates the heaviest elements in nature. Gold, platinum, uranium, the atoms that cannot form in stars but only in collision. What we see from Earth is a brief flare, lasting hours or days, glowing faintly in distant galaxies. What we hear, if our instruments are tuned correctly, is a ripple in space-time. These events are rare but powerful. They reshape galaxies, they seed worlds, they change physics, and most incredible of all, we saw one. In 2017, scientists observed gravitational waves from a neutron star merger. Just seconds later, telescopes around the world recorded the flare of the kilonova. It was the first time humanity witnessed the same event through light and through gravity. A true multi-messenger signal, a cosmic harmony. And so, two stars ended, but their ending was not silence, it was creation. After the flash fades, after the gravitational wave has passed, the sky grows quiet again. But the universe is forever changed. Where once there were two neutron stars, there is now a single object, massive, spinning, and unstable. For a few precious moments, it may remain in a state we barely understand. A hypermassive neutron star trembling on the edge of possibility. Its core churns with rotational energy, its magnetic fields twist into chaos, and then in silence it may vanish. The object collapses into a black hole. The boundary between light and gravity is crossed. No signals escape, no pulses reach us. All that remains is the shadow of its presence, the gravitational wave it left behind, and the elements it scattered into the stars. Around the site of the merger, clouds of hot, radioactive material expand outward at tremendous speed. This material is rich in neutrons, and in the extreme environment created by the collision, it undergoes our process nucleosynthesis, a cascade of nuclear reactions that build heavy elements atom by atom. It is here and only here that some of the rarest ingredients of the cosmos are made. Gold, platinum, rare earth elements, things too heavy for normal stars to forge. Each gram of gold on Earth, each trace of platinum in a circuit board, each atom of iodine in your body, likely passed through this crucible, created in seconds, scattered over light years, and swept into the dust clouds that would become solar systems. And eventually, us. You are walking around with the memory of a neutron star collision inside you. And that is not poetic invention. It is astrophysical truth. From death, creation. From collapse, abundance. These collisions, though rare, shape the chemical evolution of galaxies. And now, with modern instruments, we can observe their echoes. We map their light curves, analyze their spectra, trace the fingerprints of the elements forged in the blast. And we listen. Gravitational wave detectors scan the sky constantly. Radio telescopes sweep the heavens for signals. Satellites watch for gamma-ray bursts that may hint at another merger unfolding in some far-off galaxy. Each detection is a message from deep time, a story written in mass and motion, a reminder that the universe is not quiet, but alive with change. And yet, even as we learn more, mysteries remain. What determines whether a merger becomes a black hole or a new, stable neutron star? How much gold is really formed? What do the collisions look like from within? How does space itself behave under pressures we cannot recreate? These are questions without final answers, but the search itself brings meaning. Somewhere, in a distant galaxy, two stars are spiraling inward. They do not know we are watching, they do not know we are waiting, but soon they will meet, and the universe will shine again. We have followed the stars to their end, through fusion and fire, through collapse and rebirth. We have seen the creation of neutron stars, their pulses, their quakes, and even their collisions. And still, the question remains, what lies within? Inside a neutron star, deeper than the crust, deeper than the sea of neutrons, there may be something stranger, something more fundamental than the particles we know, something that rewrites what it means to be matter. This is the domain of quark matter. Neutrons, like protons, are made of smaller parts, tiny point-like particles called quarks. In ordinary matter, quarks come in groups of three, bound tightly together by the strong nuclear force. But under the extreme pressure found in a neutron star's core, those boundaries may dissolve. The neutrons themselves may fall apart. Instead of particles stacked together like marbles, matter becomes a fluid of quarks. Up quarks, down quarks, perhaps even strange quarks, all swimming freely in a dense quivering sea, bound not into nuclei, but flowing in continuous contact, too compressed for individuality. This state is called quark-gluon plasma, and it may exist in the core of neutron stars. We have glimpsed it briefly on Earth, in particle accelerators like the Large Hadron Collider, where gold atoms are smashed together at nearly the speed of light. For a few trillionths of a second, the collisions produce temperatures and densities similar to those just after the Big Bang. And in those brief moments, quark matter appears. But in neutron stars, it may endure. Trapped within the core, stabilized by pressure, a quark heart could form, a region where matter forgets its previous shape and becomes something more elemental. It may behave like a superfluid. It may carry color charge. It may host phases of matter that have never existed in the history of the visible universe. And if the entire star transforms, we would call it something new. A strange star, made not of neutrons but of strange quark matter, a theorized state where up, down and strange quarks balance in perfect compression. Some physicists believe strange matter is stable, or even more stable than ordinary nuclear matter. If that is true, then the universe may contain not just neutron stars, but a hidden population of strange stars. They would be nearly indistinguishable from the outside. Same size, same mass, same gravitational pull, but inside, everything would be different. No neutrons, no crust, only a dense exotic core, smooth, fluid, timeless, a quark ocean wrapped in quantum rules, spinning through the galaxy in silence. If strange stars exist, they may even convert normal matter. A rogue strangelet, a small fragment of strange matter, might drift through space and trigger a chain reaction, converting other neutron stars it touches. One becomes two become four, a cosmic contagion of compression. We have not yet seen this, but the equations suggest it is possible. A star, silent and steady, carrying within it not atoms, not nuclei, but the very building blocks of reality, flowing freely, bound by gravity and the strong force, a heart of quarks, spinning in the dark, waiting to be found. If strange stars exist, how would we find them? They do not shine in special colours. They do not pulse differently from neutron stars. Their mass, their radius, their gravity, all appear nearly the same. To the eye, they are shadows. To the telescope, they are mysteries wrapped in silence. But in physics, even silence can speak. One clue may lie in the mass-to-radius ratio. Strange stars, being slightly more compact, might show up in careful measurements as just a little smaller than they should be, a little heavier than expected for their size. If we can measure a neutron star's mass and radius precisely enough, we might catch a glimpse of something beyond the neutron boundary. Another clue might come from thermal behavior. Strange stars could cool differently. Their interiors, made of free quarks, might conduct heat more efficiently, or radiate it away at different rates. Observing how a compact star dims over time, especially in X-ray wavelengths, could point to a different kind of core. There are also spin limits. Neutron stars cannot spin faster than a certain threshold. Beyond that, they would break apart under centrifugal force, but a strange star, being more compact and more tightly bound, might survive faster rotation. If we ever detect a pulsar spinning above the known neutron star limit, it may not be a neutron star at all. It may be something stranger. And then there is the idea of strangelets, tiny fragments of strange matter, ejected in cosmic collisions, drifting through space like invisible seeds. If they were to pass through a neutron star, or even a normal atomic nucleus, they might catalyze a transformation, triggering the birth of a strange core. Some theories suggest this might already have happened. Others propose that if strange matter is truly stable, it may be the true ground state of matter, and everything else we know is just a temporary arrangement. Atoms, nuclei, neutron stars, all impermanent forms waiting to collapse into something deeper. It is a haunting idea, but not a fearful one, because this, too, is the universe expressing itself, always deeper, always stranger, always more to know. Physicists are building better tools to study these possibilities. New X-ray observatories, gravitational wave detectors, telescopes that can watch stars spin and quake from light years away. Each new pulse, each unexpected fluctuation, might hold the fingerprint of a quark core. But we are not there yet. Strange stars remain a hypothesis, a possibility supported by mathematics, but not yet confirmed by the sky. And so we continue to wonder, we continue to look, and perhaps that is the gift of these stars. They remind us that we do not know everything, that inside the densest objects in the cosmos, there may be another layer, another form of matter, another kind of star, another secret waiting to be found. Let your mind drift beyond atoms, beyond neutrons, beyond structure, and imagine a heart of quarks, dreaming in the dark. A neutron star is already a limit, a balance point, a compromise between the inward pull of gravity and the outward push of quantum mechanics. between the force that collapses and the principle that refuses to let matter be crushed into sameness. But like all balances, it can be tipped. Add just a little more mass, not much, perhaps a quarter of a sun, and something changes. The equations break, the pressure becomes too great, the quantum walls give way, and the object that held itself together through impossible density falls inward forever. There is a boundary in the universe where escape becomes impossible, not because the mass has changed, but because the curvature of space-time has reached its limit. This is the event horizon, the invisible shell around a black hole beyond which nothing can return. Not matter, not light, not time as we know it. When a neutron star crosses this boundary, it leaves behind no trace. The spinning, the field, the quaking crust, all collapse inward. The surface is lost, the structure dissolves. What remains is mass, spin, and a shadow. A point where the known rules fade and the unknown begins. This is not a place in space, but a place in geometry. It is what happens when gravity wins. The limit at which this occurs is known as the Tolman-Oppenheimer-Volkoff limit. It is the maximum mass that a neutron star can carry before no force, not neutron pressure, not strange matter, not quark degeneracy, can stop its fall. We do not know the exact number. Somewhere between 2 and 3 solar masses, a delicate threshold that determines the fate of entire stars. And what lies within the event horizon? We do not know. The singularity is not a place we can see or measure. It is where the math diverges, where time and space collapse together. Some say it is a point. Others say it is a ring. Some believe the laws of physics rewrite themselves there, hiding the truth behind the veil of gravity. What we do know is this: the black hole that forms remembers nothing of the neutron star it used to be. It keeps the mass, the spin, the charge, but not the texture, not the layers, not the quark heart, or the spinning crust, or the glowing pulses. It becomes something simpler, something quieter, a silence so perfect that it traps even light. And yet, there is beauty in that silence. The black hole is not destruction, it is completion, the final act of a star, the place where matter ends and space-time begins to fold inward. It is the universe at its most absolute, its most certain, a place beyond escape, but not beyond imagination. A star once burning, then spinning, then silent, and finally, no longer a star at all. The neutron star has reached its limit, its mass too great, its pressure too high. The crust has shattered, the neutrons can no longer resist. What was once a spinning remnant of fire and fusion now falls inward, past the boundary where space folds in on itself. A black hole is born. There is no explosion, no flash, no cry. The surface vanishes, the pulse stops, all light curves inward, swallowed by the gravity it once escaped. From the outside, the collapse appears to freeze in time. The falling matter slows, redshifts, fades, until it simply disappears. And yet it is not truly gone. It leaves behind gravitational memory. If the neutron star had been spinning, the black hole now spins. If it had been in orbit, the black hole continues to orbit. The ripples in space-time that radiated during its collapse move outward forever. They travel through the galaxy, through clusters, through cosmic voids, eventually brushing past detectors on Earth. In 2015, the first gravitational wave was observed, not from neutron stars, but from the collision of 2 black holes. Their final spiral and merger sent a ripple through space, stretching Earth itself by a fraction of a proton's width. That detection proved what Einstein predicted a century before, that space is not still, and that the collapse of massive stars is not silent. We do not see the black hole directly, but we see its influence. We see stars orbiting empty points, moving under the pull of something dark and invisible. We see jets of matter twisted into spirals as they fall into the abyss. We hear the final chirp of a neutron star's song as it crosses the event horizon and leaves only gravity behind. Sometimes we catch the last flare. When a neutron star collapses, its final moment may release a burst of radiation, a faint X-ray, a shock of gamma light. The light may be brief, the heat intense, the signature complex. But with modern instruments, we can capture it. We can tell when and where a star gave in to gravity's call. And though we may never look inside, we can still learn from the outside. Each black hole tells us about the star that made it, its mass, its spin, its story. And by counting them, by studying their signals, we build a map of collapse, a chart of where in the universe matter has passed the final line. But not all neutron stars meet this fate. Some remain just below the limit, spinning quietly, pulsing for millions of years. Others merge into new stars. Some fade entirely, their heat and light lost in the dark. And a few cross the boundary. And so the neutron star becomes legend. Not in name, but in absence. A memory kept in mass, a curve in space, a silence that sings through its effect on everything around it. Neutron stars do not shine like the stars they once were. They have no fusion, no glowing surface, no solar winds. They drift in silence, cold to the eye, invisible to ordinary sight. And yet, we know they are there. We feel their pull. We hear their pulse. We see the way they disturb the space around them. They are ghosts, yes, but not alone. Many neutron stars live in binary systems, orbiting another star. Some share their life with a white dwarf, a small pale ember of a once larger sun. Others dance with companions still burning, still radiant. And some, rare and dramatic, orbit other neutron stars, their lives locked together from collapse to collision. We find them by watching the visible star. It moves in ways it shouldn't. It wobbles, it accelerates, it dims or brightens ever so slightly. These motions betray the gravity of something unseen, something dense and close. When we map the motion precisely, we discover the signature of a compact companion. In some systems, the neutron star steals matter. Its gravity is so intense that gas from its partner is pulled across space, spiraling inward in glowing streams. These streams form accretion disks, rings of hot plasma that whirl around the neutron star at tremendous speeds. The friction is immense, the temperatures rise, and the disk begins to emit light, not soft starlight, but X-rays. These are X-ray binaries, and they are some of the brightest X-ray sources in the galaxy. We do not see the neutron star directly, but we see the way it feeds. The infalling gas lights up the surroundings. Jets of matter may burst from the poles, like twisted flame erupting into space. The magnetic field sculpts these outflows into beams that flicker with each rotation. In some systems, these beams sweep across Earth, creating pulsars that also shine in X-ray or gamma light. Other companions give less, but still reveal much. Some neutron stars have no accretion disk, no dramatic jets, only a quiet gravitational tether. But even here, the motion of the pair can be tracked with exquisite detail. Pulsars in binary systems send regular pulses. As the neutron star orbits, its motion causes the pulses to shift in frequency, a Doppler effect written in starlight. By studying these shifts, astronomers have measured orbital changes as small as a centimetre per year. They have tested the predictions of general relativity. They have watched as gravitational waves carry away energy, bringing the two stars closer, ever closer, until they eventually collide. And there are other ghosts too. Some neutron stars drift alone, born in asymmetric supernovae that kick them into space. These runaway pulsars speed through the galaxy at hundreds of kilometers per second, cutting trails through interstellar gas, their bow shocks glowing faintly in infrared light. Even without companions, they leave a mark, a trail of influence, a bend in the dust, a ripple in the radio sky. They're hard to find, but not impossible, because gravity never lies, and mass, even hidden, will always pull. Some stars are found not by their light, but by their effect, by the way they change what surrounds them. And even in darkness, they can be known. Some neutron stars spin with ordinary rhythm, once every second, maybe twice, a slow, steady pulse that echoes across the sky. But some spin faster, much faster, hundreds of rotations per second, so fast that if you placed a grain of dust on the surface, it would be hurled around the star faster than a bullet. These are millisecond pulsars, the most precise clocks in the galaxy, and among the oldest neutron stars still shining. They do not start out this way. They're spun up. In tight binary systems, where a neutron star orbits an ordinary star, matter sometimes spills over from the companion. As it falls inward, it carries angular momentum, like a potter's hand, accelerating the wheel. The neutron star absorbs this spin, gaining speed until it reaches a new equilibrium, a new rhythm. Once spun up, it begins to shine, not with heat, but with precision. Each rotation sends a beam of radio waves into space, and if those beams cross Earth, we receive them, like the ticks of a metronome, each one spaced by thousandths of a second, and they do not miss a beat. For years, for decades, their timing is so reliable that we can use them to track motion across the galaxy. If a gravitational wave were to pass between us and the pulsar, it would stretch space just slightly, enough to shift the timing of a pulse by a fraction of a microsecond. By watching many pulsars at once, scientists can build a galactic gravitational wave detector, made not of wires and mirrors, but of dead stars. This is called a pulsar timing array, a network of quiet giants, spinning in the dark, whispering their pulses across light years. Every shift, every tick becomes a data point, a clue about the structure of the Milky Way, the motion of the solar system, the existence of cosmic ripples we cannot see any other way. They may even become our future compass. In deep space, far from Earth, far beyond the reach of satellites and radio towers, we will need new ways to navigate. One idea is to use pulsars. Their timing is universal. Their positions are fixed. A spacecraft, equipped with the right sensors, could triangulate its location by reading the timing of millisecond pulsars. A celestial GPS, written into the bones of the galaxy, all from the corpse of a long-dead star, spinning in silence, waiting to be read. These neutron stars, once seen as exotic and rare, are now becoming instruments for measuring time, for mapping space, for studying gravity. They remind us that what was once thought lost can still serve a purpose, that what seems inert may be filled with rhythm. The universe is not just what we see, it is shaped by things that leave no light behind. For decades, scientists stared into the cosmos and noticed a troubling absence. Galaxies spun too fast. Clusters of stars moved as if pulled by invisible hands. And between all the shining things, stars, gas, planets, something was missing. Gravity was misbehaving, or so it seemed. There had to be more mass than met the eye. Some whispered of hidden matter, dark and cold. Others looked smaller, deeper, into the very particles that make up everything. And among them, one stood out, silent, nearly massless, and everywhere. The neutrino. It was born in fire, in fusion, in the heart of every star. It slipped through planets, through people, through the Earth itself, without stopping. A ghost of the quantum world. For years it was believed to be massless, a flicker, a shadow, moving just shy of light speed. But the numbers didn't add up. The neutrino came in 3 flavors: electron, muon, tau, and if it could change between them, as some suspected, it could not be weightless. Then came the proof. A beam of neutrinos, launched across Japan, arrived at its destination, transformed. What left as one flavor arrived as another. And so, the ghost had mass. Tiny, yes, but not zero. The standard model, the great blueprint of particle physics, had to be revised. The door to new physics creaked open. Still, the mystery of missing mass was far from solved. Neutrinos, though many, are too light to account for all the gravity we see. The bulk of the hidden mass must lie elsewhere, in something even more elusive. Dark matter, another shadow, another silence, but the neutrino remains a key, proof that the universe hides secrets even in the smallest corners. It taught us to question certainty, to listen to whispers, to measure what should not be measurable. And in doing so, it reminded us, the cosmos is more than stars and space. It is also what hides between. You've listened well, Voyager, through questions older than memory and silences deeper than space. You've walked beside physicists and poets, traced signals through galaxies, and wandered down corridors where even the light holds its breath. And now, The sky stretches quiet above you once more, not as a mystery, not as a question, but as a companion. If the stars are silent, they are not empty. If the cosmos is quiet, it is not cold, it is patient, listening, becoming, just like you. And as your thoughts drift like stardust, let yourself rest in the knowing. That wonder is its own answer, that curiosity is a kind of love, and that even alone, especially alone, we are luminous. Close your eyes and feel the weight of the stars dissolve. You're safe, you're small, you're infinite. And above all, you are not lost. You're exactly where you should be. Here on this blue world, spinning quietly beneath a sky full of stars. Good night, Voyager. Dream well.